FEMs. No, so you are able to see the slides, right? You are able to see now?
Yes.
Okay. So anyway, so in the last class, we have started our stochastic FEM. Okay. So like anyway, it's a very simple FEM only. So only thing, you have to calculate the derivatives. Okay, that is the most important thing. For that, you can use the perturbation technique as already, we showed you also. Or if it is a nonlinear set, then you may have to do it in a iterative kind of framework. So these equations, you may have to solve actually. Okay. And then finally, what we are saying is, the stochastic, this FEM says essentially, reliability analysis is you have a performance function, and you have, this R, S, and other things will be there. So you will write these type of expressions. So your finite element equation is basically Ku is equal to F only. So now, because you are Young's modulus, or if you may be treating, say, several random variables. So now the only thing what you have to do is you have to find out the derivatives actually, okay, of this S or resistance or something like that. So if you know how to find out the derivatives, so how we are finding the derivatives, you remember how to find out derivatives in our stochastic FEM, what method we are using? See, to find out derivatives, what is that we are using, like dou G by dou Y1, say, what is that we are using? We are just using the chain rule of, see, we are just using the chain rule of differentiation, okay? So if you know the chain rule, say, so then you can easily find out this, the derivative. So you can see, last class we have done, dou G by dou Y1, dou G by dou Y2, Y3, how to find out these derivatives. So then, so if you know how to find out the derivatives, so then it is straightforward. So you can use your Haushofer-Lint same algorithm, say. So there, you have to put our finite element, this things itself, okay? So this is what you see we explained in the last class also. Anyway, this is required and not required. You can find out stiffness matrix and other things. You say automatically things will be done basically, okay? So now just to demonstrate or, to show this one. So if you take any frame element, say, okay? So you would have seen in your finite element course itself, the stiffness matrix and others. So you know, right, the frame element. So I think the frame element is like this. So you have, 1, so 2. So these are all the degree of freedom. Okay. So then we have 4 at this node, then 5, then we have this 6 actual. Okay. So and then there is some load is acting at an angle, some nu or something like that. Then you also can have a distributed load also. Okay, so which is acting on this element, and the angle is tau set. So this is a frame element. Okay, 6 degrees of freedom is there, and these are the loads basically. So now right, the stiffness matrix for this frame element. So since it is 6 degree of freedom, so what will be the stiffness matrix size? For this frame element, say. So what will be the stiffness matrix size? In your FEM you would have studied, right? No. Now, what is the size of the stiffness matrix? If the degree of freedom is 6, say, so your stiffness matrix size will be
6 by 6.
6 by 6 actual. Okay, so you will be having right A, B, C, something like this, minus, and stiffness matrix is always no.
Symmetric.
So it is a symmetric kind of thing itself. So you will be having minus A, minus B, then minus B, minus D, then C, some E, then minus C, minus E, G. So this stiffness matrix you can easily find out in your finite element textbooks. Okay, minus B, minus D, minus E, C, E, G. Then A, B, minus C. Then we have B, D minus E. Then we have minus C, minus E, F actually. So this is our 6 by 6 stiffness matrix. You can write in terms of some constants actually. And if the angle inclination is theta, say, so the expressions are also available in the finite element textbook. So A is some 12 EI, okay, by LQ sine square theta. So plus we have EA by L. cos square theta. So then B say this is AE by L minus 12 EI by L cube. So this is sine theta cos theta, and then we have C, that is minus 6 EI by L square sine theta. Then D will be D will be same, more or less same as A, but slightly different. So 12 EI by L cube cos square theta plus AE by L say sine square theta, and then E is 6 EI by L square cos theta. So then F say is 4 EI by L, and then G is 2 EI by L. So this is our stiffness matrix actual. Okay, so A, B, C, this one has been given. Now E anyway is Young's modulus, A is area of cross section, and theta set is angle of inclination basically. So this is inclination of the element. So with respect to the global the coordinates. So this is the stiffness matrix actually. So this D, this is our theta actually. So this is our angle, whatever you have. So that with respect to this one say, that is the angle basically. Okay. So now here, so this is how the stiffness matrix looks like. Now if you want to do stochastic FEM say, so now let us say we write as E as a random variable, I, all of them are random quantities say. What is that you require? If you say that these are all random say, and then you want to do reliability of this type of structure, so what else you require? Extra things, like last class we told, right? Compared to conventional FEM say, so in stochastic FEM, what extra information you require?
So we need partial derivatives.
So partial derivatives with respect to what? No, partial derivative is fine, but with respect to what you want? See, what are the, with respect to what? Yeah, we have to find out the partial derivative with respect to what quantities?
Transformed variable.
Transformed variable, but what transformed variable? What are you transforming essentially? See, there in the thing,
Equivalent normal.
Equal and normal is fine. See, what are xj, 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 these kind of things. So they are anyway, what are xj finally, so this x is anyway the transformation, y is a transformation we are saying. What is x? So in this problem also we have done, right? So in this problem also, when I am doing this one, so what is this x? X is x consists of? No. See in this problem, what is x here? No. See, what are these things? So in this problem, limiting strain, load, and then Young's modulus we have taken. So we are assuming that they are all, no, what type of variables they are? See, what type of variables they are? They are deterministic or stochastic they are? See, what type of variables they are, like this derivative you have to do with respect to normal, whatever you have told, fine. But you have to do derivation with the derivative with respect to what?
Random variables.
Random variables only. So that means, suppose if I say EI as random variable, say A is also random variable, say. So now you have to find out the derivatives basically. So what derivatives you have to find out? So your stiffness matrix is there, say. You have to differentiate your stiffness matrix with respect to all the random variables. Suppose Young's modulus is random, say. So this you have to find out dou K by dou E, then dou K by dou I. If moment of inertia is random variable, so this derivative you have to find out. Then if I say area is also random, say, so then this derivative has to be found out actual. Okay, so in ordinary FEM, no need to calculate the derivative, but since it is a stochastic FEM, say, so apart from that stiffness matrix, now you have to differentiate with respect to Young's modulus with I and then with respect to A. Now these derivatives are easy to find out, or how do you find out derivatives? So dou Ke, say, by dou A or dou E. This I have to find out actually. Okay, so what is that? How do you find out? No. So all the elements in your stiffness matrix say. So now you have to differentiate with respect to the Young's modulus actually. Okay, so that means dou small a by dou E, dou small b by dou this one. So all these things have to be found out. So now what happens to the derivative of a with respect to Young's modulus? So this simply becomes so 12 12 I by L cube sine square theta plus a by L say cos square theta. So this is dou small a by dou E. So you have to differentiate actually in this fashion, all those elements itself say, and then you have to form these type of matrices also. So you have to differentiate each and every element in the stiffness matrix with respect to the random variable. So this you have to compute actually. So once you know this one only, so you can see that the equations which we wrote in the previous the class. So you can see, so this is our derivative dou k by dou xj. Xj is nothing but you see your random variables. So this you have to find out because you will be using everywhere actually dou k by dou xj, dou k by this one, So of course stiffness matrix is there. So k inverse that will be fine. So at many places you have to differentiate your stiffness matrix. So this you have to compute actually the extra the information from this frame element actual. Okay. Now how do you find out the load vector? See now in this case the load also we may be having. So the load also consists of some the load itself is random. Say some randomness is coming. So in finite element what do you do? See like for example I have written P here. Okay. So now this how do you handle the load basically in FEM? See some load is acting on your beam. Say what do you do in FEM? What do you do with that load? See how do you handle load in FEM? See if there is a load here, say P is there. So how do you handle the concentrated load in FEM? You will apply at what point?
Apply nodes.
You will apply at the nodal points only. So now if you want to find out derivatives, say, so here in this problem, let us say this concentrated load P is applied at this particular node. So now you may have to find out, dou P also. So now this derivative, what happens? So what is the derivative at this point? See P is at an angle of nu basically. Okay, some angle is nu. So now you will be having a P cos nu, P sin nu, you follow, right? In X direction, Y direction, you resolve. So now you have to find out is dou F by dou P itself. So what will be the derivative of dou F by dou P? So dou F by dou P will be simply, so both the components, if you take a cos nu in one direction, sin nu in one direction. Now what about the derivative of P with respect to this node? So at this node, any load is acting.
No, sir. It will be
So the
zero.
derivative will be
Zero.
0 only. So now you will be having load vector will be there in FEM say. So there also you find out this one. So wherever the load is not there, it will be 0. Wherever the load is there, say you differentiate with respect to P, and then you can find out all the derivatives actually. Okay. So essentially stochastic FEM is there is no difference between ordinary FEM and stochastic FEM. Only you may have to find out all the derivatives with respect to the random variable. So this you have to remember. Okay. So this you may have to write down some small subroutines say. Okay. So where the derivative information will be provided in our code itself. So with respect to the load or whatever, you can find out, and then you can solve this analysis also. Okay. So now if you see this Haldar Mahadevan textbook, okay, I hope all of you have the stochastic finite element method. So he has given so many, the problems, okay, because this you have to do it in a, numerically only. We cannot do, a closed form or whatever. So he has given one nice example. I suggest all of you, you write a MATLAB program because you have to do iterative kind of a format for this problem, so he has done this problem. Okay, so you have dead load and live load, so the steel frame he has solved. Very nice this one. So D plus L. Then you have this way, this wind load. I think this is okay. So this wind load is also W, and then he has given all the these elements, the dimensions, everything he has given 30 inches. I think this direction. And then he has given, and now he says that all the random variables he has given. So the D dead load is random, live load is random, W is random, area is random, moment of inertia is random, section modulus, then Young's modulus, say, then f of y. He assumes all of them are random variables only. So in the textbook, so this problem has been nicely you followed it, given here, and then he has given the mean value and then coefficient of variation and then what type of random variable it is actually. Okay, so the type of random variable he has given. So the mean value, he says, some 0.44 units also he has given in the textbook. So 0.1, then 0.05, 0.25, then 0.41, 0.37, then area is 4.41, then it is 0.05, then 68.9, and then 0.05, then 16, then 29,600, and then 39.6. So this is a 0.11, 0.06, then 0.05, and all are normal distributions except live load is type 1, and then wind is also type 1. All are normal distributions only. Okay, so this is also normal distribution. And then he has given the performance functions also. So generally in performance functions, say, so now for that you see what type of performance. So now he has done, I think, for this column basically. Okay, so he has considered axial compression plus bending also. So there are several limit states are there. Okay, so now for steel frames, say, so where do you get these limit states? Which code book you have to see? For steel frame design or whatever, say, so all the, if it is axial compression plus bending, or if it is only compression, or if it is only bending, say, so now where do you get all these limit state functions or the failure things?
So IS 800.
Mhm. Excellent. So you have to say IS 800. Okay. So they have given for tension, bending, lateral torsional buckling, all the formulas are given in the IS code. Okay. So now that formula, say, combined axial plus bending, say, so you will have this formula also. If it is lateral torsion, you have that MCR, the critical bending moment, product of EI into, that GJ plus some warping function and others will be there. So you take those performance functions, say. So then if your thing exceeds that one, it is a failure or whatever. So you find out your performance function. Okay. So you find out your performance function. So you design. Okay, this is steel frames, a combined axial plus bending kind of thing you can take here. And then because bending moment also comes here, so you find out this performance function, say. And then, yes, evaluated. Of course, he uses ASC, American, that ASC code itself, but you can use our steel code, whatever is given in our, this our IS 800 also. So then he has found out for this particular column basically. Okay, so what is the reliability analysis for this column itself? So that he has done in this problem also. Okay, now this problem how you will solve? No. So how do you solve by stochastic finite elements? What is the first step you have to do? So this framed structure, say, if you want to use our finite element. So for framed structure already, this is a stiffness matrix for a frame element. Okay. So now you have to, how right, how to solve it in FEM. So you write the stiffness matrix of these columns, beams of this frame element, and then you get your stiffness matrix, say. So now what are the random variables here? So we have said D, L, W, A, I, Z, E, F of Y. All of them are random. So my performance function will be like something like R minus S actually. Okay. So now what happens? How many derivatives I have to calculate? So the number of random variables are 1, 2, 3, 4, 5, 6, 7, 8 random variables are there. So now what will happen to my, how many derivatives I have to compute?
So 8.
So what are those derivatives? I have to find out dou G by dou D. Then I have to find out dou G by dou L, dou G by dou W. You followed. So dou G by dou E, dou G by dou F of Y, dou G by dou Z, dou G by dou whatever the things are there, E and other things also. So you have to find out all these derivatives itself. So you may have to write one more small subroutine where it consists of these derivatives, and very easy to calculate these derivatives also for frame elements. So you can track this problem, and he has given the solution also. But of course, he has used the performance function as per AIC criteria. Okay, that this one. Combined axial plus bending set, that is comes from this LRFD. Of course, more or less same as our IS only, but small correction things will be there. So some 5 times PN plus some 8 by 9 mu by 5 times B into Mn less than or equal to 1.0 if Pu by 5 times Pn say 0.2. So like that, you see he has used this limit state. So other one is Pu by 5 times 2 5 Pn plus mu by 5b times Mn less than or equal to 1.0 if Pu by 5 Pn say. Okay, less than point. In our IS 800 also some similar formula is there for axial and then bending itself. So he has formulated his performance function. Okay, so based on this criteria, say. So this is 1 minus Pu by Pn plus 8 by 9 mu by Mn. Okay, so something he has written. Followed in the textbook, it is clearly it is written also Pu by 5 times Pn if it is greater than or equal to 0.2. Otherwise, the performance functions 1 minus because two things are there, Pu by 2 times Pn plus mu by Mn. Okay, so if this is less than 2. So he takes this one, and other formulas are there. If you see code, they will give you how to calculate Pu, how to calculate Pu. Pu may be the applied load. So Pn, they will give you all the derivations actually based on the slenderness ratio and other things. The expressions are already given in the code itself. Okay. So now he has solved, and I think finally he has solved for the 3. So that is for the column 3 he has done, and finally he says he gets some reliability indexes here. After some 5 iterations, or I think 5 iterations, or maybe some 6 iterations, he gets a convergence, and he has reported the reliability also something around 3. Okay, for this type of problem, some 3.1 or something is given, and then he also obtained the design point also. Okay, so this you have to solve in MATLAB only. We cannot do this one. So all of you can try this problem. You can take it as an assignment. So you find out the stiffness matrix, this framed structure using the frame element, and then you have to write one more subroutines to find out all the derivatives, and then you do in the loop actually, that Haushofer-Lind reliability, that same program you can use. But here one more important thing is, now this problem can you use which procedure you will use for reliability calculations? You can use a Haushofer-Lind, or what is that you have to do? Something extra you have to try. What is that?
Rackwitch.
Rackwitch. Why Rackwitch? Because
2 are type 1 random variables.
So Rackwitch means what you will do. This type 1 has to be converted into
Equivalent normal random variable.
normal. Then you can use the same old procedure. Okay, so it's a straightforward. So you have a stiffness, subroutines, and then non-normal also you have to do, and then you repeat it. Say you can find out the reliability index, and my performance function is based on combined axial and bending actually. If you want to use this formula given in LRFD, that American code, or you can use our IS code formula also. There is nothing wrong actually. Okay, and you get convergence, and of course whatever thing you use, maybe reliability index, you should get more or less a close answer as 3.1. Okay, so you please try. Okay, so this is for the steel, this one you can just try with your MATLAB. So fine. So with this, this is how you can do the stochastic FEM for linear static problems. It is a simple way you can try here. Now one more important thing which we will not go into detail, but just I will mention you use this random fields actually. So this is the most the important thing in practice is of course in many of our structural engineering problems, random variable itself may be fine, but some problems may be there. Say you have to account for this random field thing also. Okay, so now what do you mean by random field? So right now what we are saying is, suppose if I am having a beam, say, okay. So now what we are assuming right now is, if I say Young's modulus is random, say. Okay, we are saying Young's modulus is random quantity or random variable. So what is the meaning of random variable? So if I say Young's modulus of this beam is random variable, so what does it mean? Now, what does it mean if Young's modulus is random variable? You remember starting classes we have defined random variable and others. So if I say some quantity is random, so what does it mean? Now, what does it mean? If I say something is uncertain, uncertain means
Many solutions.
many solutions are there or multiple things are there. So what it says, if Young's modulus is random variable, so it is something like this beam will not have one E value. So E is random means, it is something like variety of possible E values are there, or I can have several different beams basically. So I can have a same thing only, load everything is same. I can have this E1, then E2, you follow, right? Some 100 beams or 1000 beams or 10,000 beams or something like that. You see, we used to do actually. That is what the meaning of random variable. Now, random field means what we are trying to say is Young's modulus is random only, but it also has some kind of a structure, the randomness. Okay, so randomness has some kind of structure. Okay, so that means my Young's modulus in this beam, I am saying that if L is the length of the beam, say, so my Young's modulus, is not constant for the entire beam. Okay, so now when I say Young's modulus is random variable, say, so the assumption is Young's modulus is varying for each and every beam. Actually, if I take this beam, I will get one value. If I take another beam, I will get one value. But it was not varying with respect to length or something like that. But when I say is a random field, say. So what the meaning of this thing is, my Young's modulus, it also varies actually. Okay, so some type of a pattern it will have in the beam itself actually. Okay, so now it is a random. So if I take another beam also, it is random only, but it has some type of a structure. So this is what we call as the random field kind of thing itself. Okay, so this sometimes if it is varying with respect to time, say we call this as random process also. Okay, when it is with respect to time. So when it is with respect to space, say we call them as random field actually. Okay, so not only the your Young's modulus or something, even the load also will have the load also may be random field. See, like for example, if you're constructing a bridge, say in northeast or many places, long, the bridges if you are constructing. Okay, so now what happens when you are constructing a bridge? Let us say earthquake load or whatever, say. Okay, so some earthquake or whatever it occurs. So what happens? Let us say the bridge is a long bridge like 200 meter is a span or whatever here 200, 200, 200, 200 here. Whenever an earthquake occurs, say what happens to the ground motion or what happens to the accelerations at all these points? It will be random only. What happens at all these points? Actually, if I see the ground motion here and then ground motion at this pier, and if I instrument here, say. Now what happens? What you will observe? So this whether they will show any pattern or they will be completely different. Now what happens? Whether it is a random variable or random field, ground motion, say.
So it is random field motion, so ground motion, sir. There is
So
some
what do you
pattern.
mean by random field? No.
There is some pattern in the
Yeah, so now if
ground
I see
motion.
at this structure, say, okay, at this support and this support and this support, say, you will see some type of correlations or some similarities basically. Okay, something will be, they will have some type of a pattern. But if you see, like for example, say, one station is here, okay, like let us say Chennai is here and the Gujarat earthquake has occurred, say, I will record at Chennai also, then I will also record in Bhopal actually. Okay, so Bhopal also I will record something. Now, what is your comment about these two? So one is recorded at Chennai, another one is at Bhopal, basically. Okay, and now what will be the time history at these 2 points? Random field, or they will have any similarity, or they will be completely different from each other. Far away now, these two are. Now, what happens? What is your comment here? See, at far away places, say what happens? See, when things are far away, say Chennai, Trivandrum, or whatever, some far away places. So what happens here? See what happens. They will
There will
be.
be
It's
difference.
varying with respect to time.
No, they will be varying with respect to time. They are all random only. But I am asking you whether they will have some similarities between these two places.
Sir, it may not.
No, it may not actually because the distance is no.
The distance is large.
Too much actually. So maybe it may not be a random field basically. Okay, you can some randomness will be there like that. But when you're constructing a bridge, say when things are very close to each other or whatever, so automatically you will see some similarities. Not only this one, even if you measure rainfall, say. So like rainfall, if you measure like in Chennai, Adayar also you put an instrument, now IIT also you put an instrument, you followed. Besant Nagar you put instrument in whole Chennai, say. So what happens if Adayar and IIT, so they are very close to each other basically. Okay, so if it rains in Adayar, it may rain in IIT also. So, but it may not be true that if you compare Coimbatore or some faraway places, Tirupati or whatever, they will be uncorrelated. You may have rain in Chennai, but you may not get rain in Tirupati itself. But when things are very close, say, okay, so sometimes what happens is the things may be random field or they may show some type of a pattern itself. So this is what we call as a random fit. So now here what we are trying to say is your Young's modulus or loads or whatever you are having, say, they are all random. That is perfectly fine. But apart from that, the randomness is it has some kind of a pattern in the beam itself. So L is the length of the beam. My Young's modulus, say, it is a random only, but it also some type of a the pattern in the beam itself. So this is what we call as a random field actual. Okay, so now this is a very the important and the practical problem like earthquake, the spatial variability of ground motions or whatever. So here also it is basically a random field also. Even material properties also, they will show some type of a patterns, okay, when you look it into details. So this is how you have to do. Now how do we handle this random fields basically? Okay, so it's a very complicated which you have to do additional works here. So how do we handle here is like this actually. So if I have a beam, say, okay, so simply supported beam. Now what we are trying to say is I will divide this beam into some 4 segments actually. Okay, so L by 4, L by 4, sorry. This one and this one. So L by 4, L by 4, L by 4, L by 4 actual. Okay. So I will divide this into 4 pieces. Now what we are trying to say is I will calculate Young's modulus here, Young's modulus here, Young's modulus here, and Young's modulus here in this portion of the beam. In previously, when I was saying that Young's modulus is a random variable, say the assumption is E1, E2, E3, E4, say all of them are nah. If it is a random variable, so what happens to E1, E2, E3, E4? They all will be. They all will be what? Same or different, or what happens if all of them are
Different.
Uncorrelated.
Then if they are random variables, say Young's modulus in this portion of the beam, this portion of the beam, this portion of the beam. Now what will be the Young's modulus here? No, it will be same or different if it is a random variable.
It's different.
Different. How come? If it is a random variable, say random variable means what happens in the whole beam? Your Young's modulus is whether it is varying with respect to length.
No, sir. It will be same for a
It will be
particular
same actually. So if it was a random variable, it will be same. So when you say Young's modulus is random variable, that means for this beam I will have one Young's modulus. If I take another beam, say for that Young's modulus will be different. If I take 100 beams, say 100, but in the length, overall length, Young's modulus is not varying. It is remaining constant. You followed. So that is what we are calling as a random variable. Now the problem what we are trying to say is, okay, that is for each and every beam also your Young's modulus is different. But on the other hand, your Young's modulus is different inside the beam also. It is varying as a the length itself. So this is a problem which you are facing here. You followed. So now how do we handle here is, so because it is a random field, say, because it will vary inside the beam also. So basically it is something like, now in the previously Young's modulus was random variable. Now how many portions we have divided the beam? If I divide into 4 pieces, say, now in each piece my Young's modulus is different. Actually it is something like I'm having 4 random variables. You followed. It is not one random variable. Previously it was only Young's modulus was constant in the beam, and it was to vary with one beam to another beam. Now we are having in the same beam itself 4 random. Now if I take another beam, say, so this also I have to divide it into 4 pieces. And now this piece also will be different patterns comes into picture actually. So 4 random variables are there, means you have to construct a joint the random variables. You remember when we had 2 random variables, we said, right, x1, x2, the joint density functions and other things we vary. So here also we do this joint distributions. So this is a one-dimensional distribution. Okay, so probability, of course, I am writing t1, but these are all not times, they're all space only, to just have a notation. So x of t1, say, less than x. So this is our one-dimensional distribution. Then we can have 2 dimensions also, x1 t1 and then x2 t2. That means this and then this. These are the 2 joint density sets. So the probability is x of t1 less than or equal to x1, and then x of t2 less than or equal to x2. So this is a 2-dimensional. Then you can have 3-dimensional also, x1 t1, x2 t2, x3 t3 also. So these are 3-dimensional, this one. And now since we are having 4 random variables, say, so you will be having 4-dimensional x1 t1, x2 t2, x3 t3, then x4 t4. These are 4-dimensional. You see the joint density functions comes into picture actually. So these are, it becomes much more complicated. Now suppose if I divide the beam into 10 points, say, so now what happens? If I divide the beam into tens and your Young's modulus is varying with respect to length also, so how many random variables will be there? How many random variables will be there? Suppose now we have divided it into 4 only, but in reality, if 10 is there, say, then so 10 means how many will be there? So you will have, what is the dimensionality of your problem? See how if I divide the same beam, now I have divided it into 4 actually. Now suppose if I divide 10 pieces are there, and if I am saying that Young's modulus is a random field, so now what happens? So in each piece, say, your Young's modulus is different. So what will be the dimensionality?
10D.
10 dimensions actually. Okay, so this is a big headache in our the random fit. So if it shows some type of a pattern, say, then you may have to go multi-dimensional, and all kinds of issues will be there. Okay, so now here also we can define mean value. Okay, so these are one-dimensional expected value, say. Okay, so I will not go into the details. So this is the mean value. Then we can have the auto correlation also, t1 comma t2. Don't confuse, the t is not a time, it is space only, we are just in denoting it. So expected value, say, so x1 at 2 different times or 2 different spaces actually. So this one, then we can have mu ij. So that is what we are calling, they call this as the expected value, say. Okay, x at t1 minus alpha 1 at t1. Okay, x at t2, that is the second element basically, alpha 1 of t2. Okay, so this j, this is the I. Okay, these are the exponents. So this second order ensemble we can find out. So now alpha 1 1, say, t1 comma t2. So this becomes expected value x of t1 and then x of t2. So this is what we call as this one. Now what do we call this expression? No. So this is one expression. We can write even mu 1 1 t1 comma t2. Okay, so expected value of x of t1 minus alpha 1 of t1. Okay, and then x of t2 minus alpha 2 of t2. Okay, so these are our expressions actually. And now what is this? So the meaning of this is, so we are having, if I divide it into 4 pieces, I will have 4 random variables. Now this expression, what it says is I am finding the expectation operator, say for a 2 separate this one itself. So like you say, this element and this element. So what is the correlation? What is the covariance between these two? Like that, you see, we have to find out. So this expression is known as, the autocovariance function. Okay, so this is a covariance, the function. So this is how we define, and this is what we call as autocorrelation. You followed. So this is the name we give for this functions also. The word auto, why we are calling auto is basically you remember what do you mean by covariance and correlation? Long back we discussed, right? What's the meaning of covariance and correlation? Now, where did we see these quantities? See, correlation or covariance, what does it tells you? Correlation we have discussed, right, when we had 2 random variables and others.
So correlation is overlap between the variables.
Yeah, that was between 2 different random variables basically. So correlation between Young's modulus and moment of inertia, like that we used to find out. But now here what are we doing? Correlation means we are finding of the same thing only. We are finding correlation for the Young's modulus itself. But this is a 2 different elements actually. Correlation between Young's modulus at this place, and what's the correlation between the Young's modulus and this element itself. So that's why this word comes auto actually. So auto means it is a self kind of thing. So this is not the correlation between 2 different random variables, but it's a correlation between the same random variable, which is the Young's modulus between one element and another element, because things are random field itself. Okay, so this is what you see we call as a correlation, covariance, like that. We can have so many things also, third moment and other things also here. So now to handle these things, we also use one more thing, that is a stationarity. Is a very important the concept. Stationarity or sometimes homogeneous also. Okay, so we define like this. So if I have a probability density function, say, okay, so at x comma t, so this is my probability distribution or density function I have. Now this probability distribution function, say, it remains the same actually. Okay, if I give it some small shift, so C is some type of a shift actually. So the probability density function, it doesn't change actually. Okay, it is not changing with respect to time. So what we are trying to say is, because E1 is a one random variable, this is another random variable. These are all random variables basically. So all of them will be having their own, the probability distribution, density, joint function, so many other things will be there. Now suppose if I take the one dimensional set, that is a probability density function for E1 on this element, on this element, on this element, on this element. Now it is going to remain same actually. If I shift it by some C, okay, so this we call as, you see, the homogeneous so we call this as a homogeneous or stationarity, okay, of first order basically. So now similarly for the 2 dimensions, say, so probability x1 comma t1, x2 comma t2. So this also, if I write this as a probability of x1 comma x2 and tau actually. So this tau is anyway t1 minus t2. Okay, so originally it is a t1, t2, x2, t2 will be there, but now we have it is not varying with respect to times, but it is a function of only small shift actually. Okay, this one, so then we call this as so this is tau. So this is a t1 minus t2. We can write this as a distance actually between 2 locations. Okay, t1 and t2. So then if we make this type of assumptions there, so the advantage is expected value x of t. So because it is only depending on this one, so this becomes constant, and you have the correlation function x of t plus tau, and then x of t. Okay, so this becomes r of tau. So because everything is varying with respect to tau, so this we call this as the auto correlation function actually. So it doesn't depend on the thing, but it depends only on the lag. Okay, so this is a tau. We also call this as a lag actually. Okay, that means a T1 minus T2 kind of thing we have. So it depends on the lag. So this is what we call as autocorrelation. Now, if you take Fourier transform, say, of autocorrelation, we call this as a power spectral density also. No need to worry, just I'm telling you should know at least these names actually. Okay, so the mathematics may be this one. So these are something like power spectral density. So these are the words one uses in random fields. Now here the most important thing is in what way, how we have to do it in a stochastic FEM basically. So how do we incorporate these type of random fields actually? Okay, so there are two methods which are widely used here. One is a midpoint method, they say. Okay, so these are some, and then other one is spatial average. So what it does is, so if a beam is a random field, say, what you have to do is you divide actually. So if Young's modulus is a random field. Yeah. So what you will do, so this is my beam, say, if it is a random field and it has some type of a pattern or whatever, so you divide this into infinite element. What you will do, you will divide this beam into some elements actually. So 4 elements you have divided this beam into this one. Now the Young's modulus, say, in this 4 elements it will be different actually. Is different for different element. And if it is the Young's modulus, if it is varying something like this, say, something like this. Okay, so this is my Young's modulus. It is varying randomly and it has some type of a pattern, say, with respect to this one. So what you are doing is you divide this into these places and then you find out the midpoint method, we say. So the Young's modulus in the first beam, say, it will be simply the Young's modulus which at 0.125 L actual, and then in the second element, say, it will be 0.375 times L itself. So and then the third element, say, Young's modulus of is 0.625 times L, and then the fourth element. So this will be 0.875 times length actually. So now this is my random field somebody has given you, say. So now what you are trying to do is, now you are dividing in this into 4 elements basically. So the element size is L by 4, L by 4, L by 4. So now in this random field, so Young's modulus is varying, say, among this one. So you pick up the value of the random Young's modulus at 0.125 times L actual. So that you assign for this element. And E2 should be, you measure at 0.375 times L. So you take whatever value has been provided. So the element will give different this one. Now similarly E3 and E4 actual. Okay. So now once you know this E1, E2, E3, E4, so for all these elements, so now the problem is more or less a deterministic problem. Only thing is Young's modulus is varying for all the elements. So now you do our finite element analysis and then you can do reliability or whatever, whatever you have studied previously, say. So you can calculate these numbers itself. Now this is one way. So this method is known as a midpoint method and it is very easy and it is a straightforward actual. Now another method what they use is spatial average. Okay, so this is another method. So what we try to do is, so the Young's modulus is random field only, something it is varying, say. So now you divide this into pieces. Okay, so now here in the previous method we were taking only a particular value here. So this method you do average actually. Okay, so 1 by times L by 4, 0 to L by 4. Now your Young's modulus, which is a function of space, so dt. Okay, now E2 is 1 by L by 4. So this remains same, L by 4 to L by 2, E of t dt. Okay, and then E3. So this is 1 by L by 4. So L by 2 to 3L by 4. You integrate this term, E of t dt. Then E4. Okay, 1 by L by 4. So then 3L by 4 to L by 4. Sorry, L, now the last element actually, okay? So L itself, so E of t dt. So what here you are trying to do is, you are averaging basically. So you're averaging over this element, whatever value is there, and then, you take your finite element program. So now you take E1, E2, E3, E4, and then you do your analysis. The same, the reliability analysis, you have to use it actually. Okay, so this is one, the famous methods which are widely used, to handle this random fields. Now there are other methods also where the how to handle the random fields, Karhunen law of expansion, other kind of techniques are there, but that requires a lot of the mathematical background actually. Okay, so now in they have one sometimes whether Young's modular should be a random field or a random variable, whether you have to model as a random field or a random variable. So this you can whether it is really required, you followed. So many things are interesting things one can do, okay, while doing this stochastic FEM also. Like so one there are like you have to do it in so many numerical way, like how what should be my element size. So what should be my element size and what should be my random field discretization. Okay, so what should be my discretization of the random field? So random field discretization will be different. Your element size will be different. So how do we handle all these things? So this becomes very interesting kind of thing itself. Okay, but of course it requires a lot of the mathematical background about random field, stochastic processes, and other things. So so that requires some more details actually. Okay, so I think whatever we discussed until now, up to the framed structures, that is almost more or less same for your for as far as this course is concerned. So if some of you are interested, say, so you can go through textbooks, or you can see, you can easily follow it. If the things are random fields, how do we handle these type of problems? But you may have to have a knowledge about the stochastic processes, and then the higher order densities, autocorrelations, the power spectral density functions, and other things are required actually. Okay, so anyway, so I will stop here. So as far as this course is concerned, sir, whatever we discussed until now is more or less sufficient. So if you are able to solve a framed structures, okay, frame structure or whatever, say, the stochastic FEM, that is more or less sufficient for this course actually. Okay. So if you have any doubts, we can please ask me, then we will. See, all of you are there.
Yes, sir.
Yes, sir.
Now I think so with this I think we will close our course also. I think this one. So to just summarize, whatever we have discussed until now, I will make a quick summary. Okay. So whatever we have discussed until now. So the first thing, what did we discuss? Any of you remember? What is that topics we discussed?
Probability.
Probability theory we have discussed. Okay. I hope all of you know, right? How many definitions of probability are there?
3 definitions.
3 are there. What is the one which is widely used, or what is the one we are using?
Axiomatic definition.
Axiomatic, and right, those 3 axioms that never you should forget in your life. Okay. What are those 3 axioms?
Construct a sample space. Construct event space.
And you have to
And
assign
probability.
as per. What are those axioms?
Probability of any event should be greater than equal to 0. Probability of sample space should be equal to 1. And probability of a 2 union is equal to probability of one event plus probability of second event minus probability of intersection of both.
Excellent. So this is what we discuss. Then after that,
conditional probability. This all.
Conditional probability. But anyway, all of them comes under the probability theory only. Okay. So we also discussed independence. You remember?
Yes.
Independence, mutually exclusive, all those things we have discussed. Okay, you should remember what the independence and mutually exclusive are entirely different. Okay, so if it is independence, a probability of A intersection B will be
probability of A into probability of B.
Suppose if A and B are mutually exclusive,
probability of in both intersection will be 0.
Zero. It's will be a intersection will be a null set kind of thing. There is no overlap actually. Okay. So this is what we said as a mutually exclusive. Then we discussed a random variable also. What do you mean by random variable?
Transformation or mapping.
Transformation. Okay, it is not random kind of thing. So please remember. Okay. And then here we have discussed probability distribution function, probability density function. Then what else we discussed? I think we have also discussed what are the common random variables which we encounter actually. So what is the simplest random variable we have discussed?
Gaussian.
Gaussian.
Binomial.
No, not even binomial. Before binomial, what is the simplest random variable? It will have
Bernoulli
only.
random variable.
Huh?
Sir, Bernoulli random.
Bernoulli. Why Bernoulli? Gaussian means you can have your samples. Gaussian is a simple random variable. It is the most complicated because its sample space goes from minus infinity to infinity. It is not simple random variable. Bernoulli is a simple because for Bernoulli, what is the sample space?
Just two
You can have
events.
two outcomes.
Two only. That's all. So simplest random variable. If it has only one outcome, say what type of random variable it is?
Sir, it is
Deterministic.
Deterministic. So please remember. So deterministic is one. So random, simplest random is two only. That is a Bernoulli. Okay. So we have discussed Bernoulli, binomial, then Poisson, then geometric random variable. You followed. So many things we have seen. Then exponential, then Gaussian, and then Gaussian leads to so many things actually. Log will give log normal, e to the power of x, whatever that log normal comes. Then the square of Gaussian is what? So if you square a Gaussian
Chi-square.
chi-square, then I think gamma also it is not. I think so. What is it? Student t distribution. You follow, right? So and f distribution. So many things we have discussed actually. Exponential. So many Poisson. So many things we have discussed actually. Apart from this, there are so many random variables are there. But these are some of the things which are widely used in textbooks actually. Okay, textbooks are even in our practice also. Then after this, we also have discussed about
Two-dimensional extreme.
sorry, I will come to two-dimensional. So extreme value theory also we have seen actually. So extreme value theory means what is that? We said extreme value distribution. Say. So if I have any data, say, what did we say? The data, if you try to find out the probability density function of the data, it will be Gaussian or it may be something. But if you take only the large values, say, what happens to the large values?
We will neglect the probability. It approximates to 0.
It goes to 0. So now when the data, original data is some random variable, but if you take only the extreme values, say, they will follow what distribution? How many are
There are
extreme
three
values?
types.
Three type. But what is that theorem? You remember that theorem also?
Generalized extreme value distribution, Fisher tip.
Fisher theorem. So what that theorem says is your random variable may be Bernoulli, binomial, Poisson, geometric, or anything. It may be any type of random variable. It is say it extreme values have to follow three groups actually: type 1, type 2, type 3. How did we decide type 1? Which one will come under type 1? Which one will come under type 2 and type 3? What is the criteria? Any of you remember?
Exponential tail for type 1.
Excellent. Exponential tail. Other tail is
Uh, for type 2, it's polynomial.
Polynomial tail. Type 3 is
Bounded.
bounded distribution, uniform or something. If you have put a bound, it comes in. So mathematically it is proven your data may be normal, geometric, Poisson, chi-square, or whatever distribution it is, but all their extreme values have to follow in these groups actually. Okay, there are, and the extreme values cannot follow any other than these two because based on that theorem itself. So this we have discussed. Then we have also discussed two dimensions also. Okay. So two-dimensional means the joint densities x1, x2, x1 comma x2. So here we discussed the correlation, covariance, all other things we have seen also. So this also we have discussed in our in our course. Next, what did we discuss? What else we have discussed after this?
Monte Carlo simulation.
We have discussed Monte Carlo also. It is very Monte Carlo is the most easy thing actually. Okay. So Monte Carlo simulation, what is essentially you do if you say Young's modulus is random variable and you have to do analysis say. So instead of doing one analysis, you have to do
We have to do multiple.
many times.
analysis.
So instead of testing one beam, you have to test 10,000 beams. And then among these 10,000, how many are failing or how many are this one, you can easily compute. So now in Monte Carlo also, we have discussed, I think, two important things also. What are those things? You remember the computational efficiency, to get Monte Carlo means you have to run 1 lakh or, because depending on your probability, what you are looking for, your simulations may be too much actually. What are those efficient things we discussed? Some two methods we discussed, no?
Latin hypercube sampling.
Excellent. Latin hypercube we discussed. This is a very famous technique, okay? And don't forget, in practice, we have also used many problems. As a Latin hypercube, will give very good result with few simulations. Then another one was
So assembly.
if you are interested not in this one, some just the movements, the mean and standard deviations, the Rosenbusch that you remember, 2k plus 1, that methodology, you take samples at mean m plus sigma, something like that, and then you do the computations actually. So this also we discussed actually, okay, Monte Carlo simulation. Then
Reliability.
then we directly came to reliability. Okay. In reliability also we have discussed detailed actual. Suppose if it is a normal and if things are linear say, then reliability calculations are so if the things are normal and then if it is this one say, so what happens? If the things are normal and linear, what are your reliability calculations will be easy or difficult?
Easy, sir.
See, we have given right. Where are those? So we have already, Fy into Z, do you remember? So these are the things I think we have given. Yes, sir. So this is what, we said, you followed the different probable reliability or something we have said. And when it is a G less than 0, you have to calculate or, you can do R by Q or R minus Q itself. So we have discussed all these things, how to compute the reliabilities. So if it is a very linear say, and if it is a normal, so my reliability definition is ratio of mean to sigma actually, you followed. So this is what we are calling as reliability index. So you can use a direct formula. If things are simple say, only two things only are there, R, Q, and then both are normal. Directly, you can use this mu R minus mu Q and you can calculate this numbers itself. Okay, so there is no issue if it is a normal or log normal or whatever. So you can easily calculate the reliability indices also. Okay, so things are very easy when it is a linear and other things are there. Now, when the problem comes, when the things are see, the most important thing what we said was the main headache will come when the things are
Non-linear.
so but non-linearity, how you can handle? So you can handle the non-linearity through, what is the methods we have used? 1 second, just start.
Hasofer-Lind and Rakowicz.
The Hasofer that comes later actually, but we have said right one most important thing.
By forming the function itself differently.
So now we have to use the Taylor series. You remember, right? The Taylor series expansion we use, and then we try to solve the problem. So you are able to see the screen, right? It's not moving, no?
It's lagging.
1 second. Yes. Just 1 second. Now you are able to see, right?
Yes, sir.
So now when if it is a non-linear, say, so what did we say? If it is a non-linear, still you can use our no need to do this Haushofer Lind or whatever we followed, right? So what we have said was we can expand things in. So what is
First
this?
order, second movement.
So this is a first order second. There is nothing like first order second movement or whatever. So it basically you are using a Taylor series expansion, nothing else. Okay, and you are expanding around.
So mean.
Mean
You are expanding around what value? Yeah, you are expanding around. So Taylor series
value.
around the mean value. So you can use the derivatives or whatever, and then you can compute actual. So this is what we said. And of course, the first order second movement, the first order means that goes to the Taylor series. So if you include the terms only up to first order, so that's why we are calling it the first order method. Second movement, why the reason comes is reliability calculations. We are using only mean and standard deviation only. That's why the second movement, that word comes. So if you use the second order, say, then it becomes SOSM or that kind of methods will come, okay, depending on the order. So this also we have seen in the previous class actual. But what did we say here? What was the most important thing?
When it doesn't work for non-linear and non-normal problems. Very
So when you are having, we have seen this problem, right? Suppose if I take, this limit states f by z minus pl by 4, or if I write fi minus pl by 4z, so this z I put it here. So what was happening? Mathematically, both are same only, but if the things are non-linear, say, there is a chance that you will get two different answers actually for the same problem if you slightly change the function itself. So this was a problem. So what did we say? So to avoid this one, what did we do?
We took design points and evaluated at that.
So what we are saying is, please don't expand your Taylor series on the mean value, because mean value and other things are different here. So what we said was where the design points is, that also you can treat it as unknown, and you can find out reliability and design point in one go. That is where this iterative procedure came actually. Okay. So don't expand around the mean value. So that's how we go. So that is how this Haushofer-Lind reliability index comes. And these all the expressions, whatever we have derived, say, all of them come from the optimization. Okay. So you have an optimization procedure. The constraint was this one. So this optimization, that is, you have to minimize the distance from the origin. That is Z transpose into Z. This, it is something like a square root of x1 square plus x2 square, like that only. So this distance has to minimize, and the constraint is my performance function has to be 0 actual. Okay, so we do like this f of x plus lambda times p of x. We do this one, and then it results into a set of equations and others. So this was the steps which we formulated in the previous classes itself. So here the reliability index is not known, design point is also not known, so you have to do it in an iterative process actual. Okay, so this we have discussed also. And then what we have said was that was Haushofer-Lind methodology. And then the other most important thing what we said was, if things are not normal distribution, say, so then what did we do? Yeah. So what was that method? So if things are not normal,
Like which Fisher procedure?
Rackwitz method. So Rackwitz method is same as your Haushofer-Lind only, but only thing what you have to do, all the non-Gaussian things you have to transform to
Equivalent normal.
equivalent. So this is our mathematical procedure actually. So you find out design points in your original distributions, but you have to transform them into equivalent normal, such that at that point the probability from original distribution and the probability from the normal distributions, so this remains same actual. Okay, so this is how we are computing the points. So if I have a non-Gaussian distribution, say something like this, okay, and then I have a Gaussian distribution, say. So what we are doing is, let us say this is my probability, some 0.2 or whatever, and this is a design point, so corresponding to this one. So now what we are trying to do is, now in this normal also, you are trying to find out where is my 0.2 probability. For the same probability, what is the corresponding, this point actually. So like this, you see, we are calculating. So my two probabilities are same. That is how these two equations comes, and then you can solve these two and then get this one. And once you have this one, say, then the same Haushofer-Lind thing can be used here also. So that is how we calculated these things also. And of course we have solved some problems and others also. Okay. And now, after that, what did we discuss after this rack wedge? This one.
System reliability.
So we have discussed the system reliability also. Of course, correlated also we have seen. We have not solved any problem here. But if there are things are correlated, sir, you can easily uncorrelate them through your eigenvalue analysis. So system reliability we have seen. So here also reality structures are very complex, but simple things we have seen like a series system, parallel system actually, because it's very easy to understand. So which are in series, which are in parallel. So which will be in series, which will be in parallel generally in our structures. So if the structure is statically determinate, say, what type of system it will be?
Series system.
Series, because one fails, the entire thing collapses. If it is indeterminate structure, say, it will be in parallel systems. Okay. So of course, in reality, you will have hybrid systems. Okay. You will have some in parallel, some in series. So you may have to do, hybrid things also. Okay. So some are in series, some are in parallel. We have, that frame problem, I think, which we have solved, which is available in the textbook, which is a hybrid kind of thing. Okay. So this also we have seen in our last class. Of course, you can use this variables also, Boolean variables or whatever. Okay, it got shut down. Yeah, so this also we saw in our last class. Okay, so this also we have seen, and now after this, we went towards. So this also we have seen. Oh God, this got erased. Now, finally, after system reliability, say, then we have started looking at. Now, what was the next thing we saw in after system reliability?
Different techniques means response of surface approach.
No, but why that response surface is required here?
For implicit performance functions.
So in reality, you will have explicit or implicit performance functions.
Implicit.
So we will be having, implicit, because you may be having your, it is a finite element program, or some other numerical programs will be there. So you will have you have to do these things. Okay, 1 second. Yeah, so this also we have seen that implicit cases. So what are the methods available for implicit?
Monte Carlo simulation.
So the things are, the Monte Carlo simulation is one thing we have seen. Then other one is
Response surface approach.
the response surface approach is there. Then we have this stochastic FEM. Okay, stochastic FEM is very easy, we have said. So only thing is, you have to calculate the derivatives. So you have to use this chain rule of differentiation. Okay, so these are only thing which we have said in our previous class. Okay, so all these things I think we have almost covered. So this I think we have seen all these details, or you can even use finite difference approach also to find out the derivatives, because when the things are implicit, say, the problem comes up here is to compute the derivatives in your the method itself. So for that we have seen response surface, these things can be used, and right now in people widely use this in practice, say, stochastic FEM is anyway that is perfectly fine, but in practice, if you see, have you seen any papers, what methods they are using? So if you see reliability, a lot of papers have been published actually in the literature. So if you see which is the one widely used for implicit? So in research, so many papers are there. In practice, what people are using? Now, which method is more popular? Response surface, or finite difference, or stochastic FEM, or Monte Carlo? bad. The slides, I think, they got deleted. Okay, anyway. So now the most, if you see most literature, the more widely used is
Response surface.
So if you see many papers, they use this response surface method. The advantage is, you have to do some few simulations. You fit some kind of a surface and then you do your calculations actually. Okay, that is how, this method are widely used in practice. So anyway, so with this, I think, we have almost covered, all the aspects of our course. Random field is one extra thing, but of course it requires a lot of random processes and other, so many other details are there. But of course, it is very easy to follow. Once you have done if you are thorough with all these concepts, say, that will be very easy for you to follow also. Okay. So now if you have any questions or anything, we can discuss.